All right. So before we get into the law of sines, I have some stuff from the section that we skipped because we don't know the unit circle yet to do a little proof of. So the first thing is we know how to find the area of a triangle, right? The area of a triangle is 1/2 base times height. But what if it's difficult to tell what the height of a triangle is? For instance, if I have a triangle that's like this, it might be a little difficult to tell what the height is. They clean these boards with something and it makes it really difficult to write on. So maybe a triangle like this, where we can kind of see the height, but maybe the height's been scooted over or something like that. Or we're just not told what the height is. Like that's the H. And so we want to figure out, how do we figure out the height here? The information that we need to figure out the area specifically is we need an angle, which I'll call theta, and we need two sides, which I'll call A and B. Cool. Then now we want to figure out H here. Well, I can kind of draw in this right triangle shape here, where I've got theta, A, and B. I want to find out this other side, which I'll call H. So I've got my known stuff and my unknown stuff. What relates the opposite side with the hypotenuse? Sine. I have that sine of theta equals opposite over hypotenuse, which in this instance would be H over B. All right, so just solving, I have H equals B sine theta. And now I can plug that into my area formula. So the area of the triangle equals 1/2. My base is A. And then my height is B sine theta. So for any triangle, as long as I'm given an angle between two sides, I can find the area using 1/2 AB sine theta. Cool. That's a useful one to write down. Any questions about this? Now, I have a fancy way to where I can relate all of the sides and angles with each other using a certain special prescription. I'm going to erase this H here. I'm going to actually just draw this bigger. So I have my triangle of arbitrary shape, angles, and whatever. I'm going to label all the sides A, B, C. And then for each side, the angle opposite from that side, I'm going to label, my bad, with the capital letter. So I'll label this with capital A. I'll label this one with capital B. I'll label this one with capital C. And I can gather some information about this just looking at the different things. Given my area formula, I can either say, all right, I can pick this A angle, and I take the two sides beside it. So I have 1/2 BC sine A. That's equal to the area. I'll write it with a fancy A. But that should also be equal to, let me write this on a line below it, 1/2, I'll pick this one, so I've got AC sine B. And that's also equal to, if I pick this angle, 1/2 AB sine of C. And that's just coming from this, where again we have some angle in between sides A and B. So I'm telling you that the area of this triangle can be written 3 different ways. Another thing that I could do here is I can cancel out this 1/2 in all of these since they're all equal. Not worried about that. Just not worried about area at all right now, but I know that all of these are equal to each other. And then the next thing that I can do is I can divide everything by lowercase a, b, c. Right? Since they're all equal to each other, dividing them all by the same thing makes them equal to each other. And then, doing some cancellation, I get the b and the c cancels here, so I get sine of a over a. Here the a and c cancel out, so I get sine of capital B over b. And then a, b cancel out, so I get sine of capital C over c. And now I have the statement of the law of sines. It says that sine of capital A over A equals sine of capital B over B equals sine of capital C over C. Where the angles and sides are related in the way that I've drawn this triangle. I could rotate these if I want to, but specifically, it's the side opposite from the angle when I'm making this construction. So the sine of an angle divided by its opposite side is equal for all 3 pairs of angles with opposite sides. We can do an example with this. I'm pretty sure this example is straight from y'all's textbook within the chapter. So say we're looking at a satellite that's passing over, at some point, it passes over Phoenix, Arizona. I probably spelled that wrong, I did. O-E. Phoenix, Arizona, and Los Angeles, that's a T, California. The distance between these two, we will say is 340 miles. Our satellite is somewhere up here. I'll say that's a satellite, that's terrible. I know that the angle at some point that it makes between Phoenix and the satellite is 60 degrees. And between Los Angeles and the satellite is 75 degrees. And so now the question is, at this given point in time where it makes these angles, how far away is it from Los Angeles? And we can solve this using the law of sines. So I'm going to label this capital A, capital B, capital C, and this is lowercase a, lowercase b, and lowercase c. How many degrees should a triangle add up to? 180. So if we do 180 minus 60 minus 75, that's 45 degrees here. So I know all of my internal angles, and I know at least one side, so I can figure out all of the rest of the information. All right, I'm looking for C here, and what do I know? I know that, or I'm looking for A here, my apologies. I know that sine of capital C over side length C is equal to the sine of capital A over lowercase a. Because the law of sines says so. It says that all 3 of these things are equal, so this first one's equal to this third one. All right. Now I can just plug in my known information. C is 45 degrees. It's important to notate that we're using degrees, so when we plug it into our calculator, we have it in degrees. Over side length C, which I said is 340, is equal to sine of A, capital A is 60 degrees, over side length A, which is what we're trying to figure out. Maybe I'll call it X. And now I want to solve for X. Does everyone have the stuff on the right side of the board written down? If you do not, raise your hand real quick. We're good? So the thing I'm solving for, now algebraically, is sine of 45 degrees over 340 equals sine of 60 degrees over x. To solve for x, I can multiply both sides by x. X is over here canceled. I'm left with x sine of 45 degrees over 340 equals sine of 60 degrees. And then I just multiply by the reciprocal on both sides to get rid of this fraction. So I get x equals sine of 60 degrees over sine of 45 degrees times 340. Grab my calculator real quick. Make sure I'm in degrees. I'm in radians, I need to change that. I've got sine of 60 divided by sine of 45, and then times 340. And I get 416.4 miles. So it is, at this point, 416.4 miles away from Los Angeles. That's that side length there. I could also then ask how far away is it from Arizona. I would do the same thing, but instead of sine C over C, I would use sine B over B. Any questions about this? All we've really done here is we've added a new formula to our set of formulas to use in our 5-step process. It is not always the case that I get the specific answer that I wanted, though. Remember how we were talking about how taking an inverse trig function of a number can spit out a bunch of different coterminal angles. This is where the coterminal angles come in, because there are several angles that have sine 60 or have an arc sine like this. And so we need to go through and we need to figure out which one is actually going to be correct. Does everyone have this left side of the board written down? Y'all are a bunch of sleepyheads today, aren't you? I'm also really tired. I got woken up at 5 this morning by my cats, and I didn't go to bed until 1. So I'm very tired and running on coffee. Right. Say for instance now, I'm given a triangle with a side length, or an angle of 45 degrees. Opposite from that is a side length of 7 root 2, and somewhere else there's a side length of 7. And I want to figure out all of my information here. I'm going to call this A. So this is side length A. This is capital A. I'll call this B and side length B. And I'll call this C and side length C. So I have some information that I want to figure out. Makes sense. Well, if I want to figure out, for instance, B here, I have sine of A over A equals sine of B over B. And I've got my information for this side, and I've got this side length here, so I can solve for sine B. So this is going to be sine of my angle A is 45 degrees. My side length lowercase a is 7 root 2. Let's see. I'm looking for sine B. I don't know this yet. And my side length lowercase b is 7. I'm trying to get b. I'm trying to figure out what b is. I can multiply the 7s over or just cancel them out. And I get sine b equals sine of 45 degrees over the square root of 2, which works out to 1/2. You can do that in your calculator. When we learn the unit circle, these will become a lot more useful, or a lot easier to do. So I'm looking for what angle has sine of 1/2. Well, there's a lot of angles that have sine of 1/2. We want the angle so that the inside stays equal to or less than 180 degrees. So it definitely can't be the case that whatever b is plus 145 is equal to 180 degrees, because then c would be 0, and I wouldn't have a triangle, I'd have a line. So it has to be that b plus 45 degrees is less than 180 degrees, or b is less than 135 degrees. There's a condition that we have there. And so if I put this into my calculator, I get a couple of results. If I take b equals the inverse sine of 1/2, so sine and then 1/2, I get 30 degrees. There is another angle which does this, which is 150 degrees, but I know that my answer can't be 150 degrees, because then 150 plus 45 is 195, and I no longer have a triangle. No, it's 30. Y value is the same. 180. Yeah, it's 150 degrees. So, or 150 degrees. But this is the one I had to pick to make this answer make sense. Right? Is anyone confused on why this is the one I have to pick? Because I feel like that's the important part of this example here, is that I have to pick this one.
It's less than 135.
Yeah, it's less than 135, and the reason I had to do that is because my inside, I could put an equal here if I wanted to, my inside can't be greater than 180 degrees, because I'm dealing with a triangle. Since I'm already told what one of the angle measures is, that restricts my final outcome here. So now I have what I solved for, b, and I said that it's 30 degrees. All right. What should I probably do next to get my last angle before I try to get my last side? I'm given all the information I need. I don't really have to do much math or any formulas or anything. I'm given two of my angles, and I know what they all have to add up to. So I know 30 degrees plus 45 degrees plus C degrees equals 180 degrees. 180 minus this is 150, minus that, C is 105 degrees. It doesn't look like it the way I've drawn it, but it is. This is actually a triangle that looks more like it's got an obtuse angle here. So I have C is equal to 105 degrees. And now I can solve for side length C using my law of sines. And I can either use the B pair or I can use the A pair. Which pair would y'all rather use? A. Cool. So I have sine A over A equals sine of C over C. So this is sine of A is 45 degrees. Side length A is 7 root 2. C as an angle is 105 degrees. So sine of 105. And side length C is what we're figuring out. Then just doing my arithmetic and rearranging. Multiply C to both sides, divide by that fraction. I get C equals sine of 105 over sine of 45 times 7 root 2. And I can plug that in my calculator. Let's see, sine of 105 divided by sine of 45. And then times 7 root 2. And I get 13.52. And that makes sense. With the angles I've drawn, if this is actually the correct thing, since this angle has to be greater than 90 degrees, so that's 105. That's 45 and that's 30. This side length should be the longest, and it would be. This is 13.5. This is 7. 7 times root 2. Put that in my calculator. And that's 9.9. So this is the longest side, by a good bit too. So it makes sense just kind of checking our answer for some common sense, I guess. Any questions about this example? I could also come up with an example where there are multiple correct solutions, and the interpretation might be up to the physicality of the situation, but mathematically it has two correct solutions. Who remembers in pre-calculus algebra when you did trajectory problems and there were two solutions for when the thing hit the ground? Both of those solutions mathematically are correct, but one of them is physically correct. Trig problems do the same thing. If you don't remember what I'm talking about, say I throw something off a building and I want to know when it hits the ground. It has a quadratic arc. There's two solutions for when it touches the ground, but in one of them the time is negative. It doesn't make sense for time to be negative, so we talk about positive time. Here we get two solutions mathematically, but only one of them will make sense physically a lot of the times. But I'll present just the mathematics of it. say for instance we have a triangle. Where I'm given one angle is 43.1 degrees. This side length is 186.2 degrees. And this side length is 248.6 degrees. I'm going to figure out this one and this one. Maybe I'll call this theta and I'll call this phi. And I'll call this x. Alright. Well, just using our law of sines, I already have one pair. And I can get my second pair. So setting up law of sine problems, there's kind of a method for that too. Find your pair, find what other piece of information you have to make a pair. Once you make your second pair, you can solve either for your last side or your last angle, and solve for your third pair. So here I have sine of 43.1 over 186.2 equals, so I've got that pair. The only other pair I have a bit of information about is this one. So I have sine phi over 248.6. Going over here, I have that sine of phi equals 248.6 sine of 43.1 degrees over 186.2. There's really degrees there. Degrees there. I can punch this into my calculator. 248.6, and I have sine 43.1 divided by 186.2. And I get 0.91225. I'll leave it as that. So just rewriting that last line, sine of phi equals 0.91225. All right. And then undoing this, I have phi is equal to the inverse sine of this 0.91225. Punching that in my calculator, I get 0.91225. So I get 65.82 degrees, rounding a bit. So I can put that here as my phi, 65.82. But there is also another value. Let me go over here. One thing to note is that sine of some angle is equal to sine of 180 degrees minus that angle in degrees. Or, using radian, sine of pi minus theta radian. For a quick visual proof, and we'll learn this with the unit circle, sine values correspond to the y part of a coordinate. So if I have something here with a y value, then the thing that has the same y value on the other side of the circle is 180 degrees, so this full 180 degrees, minus that angle. Again, this will be more comfortable when we do this with the unit circle, but this is one thing to recognize here, which means that there's also the solution of 180 minus 65.82, which is 114.18, or just 114.2. So there are two possible solutions. It is either that this angle here is decently pointy, it's less than 90 degrees. So it's something like this is 43.1. This is 65.82. And then this last angle would be 180 minus 43.1 minus 65.82. 71.1. So those could be my three angles. Or this one could be pretty wide. 114 is greater than 90. So it would look maybe like a little wider. So it's 43.1. This one would be, what did I say, 114.2. And then clear 180 minus 43.1 minus 114.2. And this would be 22.7. Both of these are valid descriptions of this same triangle. This could still be, one of these side lengths could be 248.6 and 186.2, and I have these subtended angles. It'd be like if I took a triangle that was shaped like this. Maybe I'll do that out longer. And I flipped this bit inside, so it actually went to here. It's just that 180 minus the angle thing. So I just flipped that part inside. This is still the same side length, I just have different angles. That's the idea there. So it depends on the physicality of the situation, whether or not one of the solutions actually makes sense or not. Any questions about this? When you go to face a homework problem or something that involves this, either the problem will say list all possible angles, or it will say list an angle within some sort of parameters. And so it'll say list an angle that's less than 90 degrees, which would give you this 65.82, or list an angle more than 90 degrees. So this is acute, this is obtuse. And so it might ask you to list your angles that way instead. Any questions about this problem at all? There are also situations which are somewhat realistic where the answer actually just doesn't exist. There is no solution of the triangle in that scenario. Does everyone have this written down? All right. Say, for instance, I have a triangle like this. This angle is 42 degrees. This side length here is 70 degrees, or 70, I guess, inches or whatever. And this side is 122. And we're asked to solve the triangle here. I've got the angle opposite to this, I might call it theta. And just from the first bit of law of sines, I have that sine of 42 degrees over 70 equals sine theta over 122. Then I get that sine theta equals 122 sine 42 over 70. Which, if you punch this into your calculator, comes out to 1.17. What is the problem with me saying that sine of an angle is 1.17? This is a bit of a sub thing. Yes?
It's it's a decimal instead of a fraction.
That's not the problem. It doesn't matter that this number is a decimal refraction. I could have written this as 8 over 7, which is approximately, yes.
Is it outside of the valid domain?
It's outside of the valid possible things for sine. Remember, sine of an angle, theta, is between -1 and 1. There's no angle that I could use which gives me that sine of that angle is greater than 1. So there's no solution to this triangle. So if you encounter a problem like this, it might say solve this triangle. If there's no solution, write no solution, and then explain why there's no solution. So the important thing to remember here is sine is bounded between -1 and 1. Cosine is also bounded between -1 and 1. So when we talk about law of cosines tomorrow, we'll also encounter something similar.
Is that the domain or the range?
That's the range.
Okay.
Domain is the values it takes in. So the domain of sine functions and cosine functions is R. It's all possible values. The range, or also known as the codomain, is everything that it spits out. So it's between -1 and 1. A lot of y'all probably remember sine or domain and range as x values and y values, which is perfectly fine. Sine function, so yes, sine of 0 looks like this, where the top of the function is bounded by 1, the bottom of the function is bounded by -1. Cosine is the exact same function, but I've shifted it over a bit. So it has the same domain and range, yes.
You shifted over by 1/4 pi, right?
Yes, they're shifted over by, specifically pi over 2. They're shifted by 90 degrees between each other, so it's pi over 2 for 90 degrees. Cool. So that's why they're bounded between these. When we graph trig functions, we'll see that a little bit more. Any questions about any of this or anything that we did today? Y'all are so dead, it's unreal. This is probably the most boring 45 minutes of your life. So, it's Monday. It'll be all right. This is only week 3. There's 13 more weeks left. So, wake up. It'll be all right. All right. That's all I have for y'all today. If y'all have any questions about anything, feel free to reach out to me. Make sure y'all are doing your homework. If you have any questions about that, you can also reach out to me. Do not use Ask My Professor because it just doesn't work apparently. I had one student ask me a question 6 days ago, and I didn't see it until today because it didn't actually send me an email. So, go in peace.